Hello everyone, today's discussion is going to revolve around a very exciting object, a magnet. But in order to discuss about a magnet, we need to know what it is. A magnet is an object with magnetic force. Magnetic force occurs in an object due to the motion of electrically charged particles. A magnet only attracts certain metals known as magnetic materials, and it also attracts the unlike poles of another magnet. As you observed when you moved the magnet near the magnetic needle or iron dust, magnetic force can act at a distance, hence it's a non-contact force. But how can you differentiate between an identical looking magnet and a magnetic material? If we touch any point of the iron bar to the center of the bar magnet, it won't attract the iron bar due to the presence of a neutral point. As an iron bar has no such neutral point, when we touch any point of the magnet with the center of the iron bar, it will attract the magnet no matter what. Thus, we can easily differentiate between an iron bar and an identical bar magnet using the neutral point of the magnet. Now, we are going to demonstrate the properties of magnets one by one. First is the attractive property. It's the attractive property of a magnet to attract magnetic materials. The second is the directive property. The directive property of a magnet is that when a magnet is freely suspended, it always aligns itself in the north-south direction. The third is that unlike poles attract and like poles of a magnet repel each other. The fourth property is magnetic induction. Let us know what it is. Magnetic induction is the process by which a changing magnetic field induces an electric current in a conductor. It's the principle behind transformers, electric generators, and many other devices. Here's how we can demonstrate magnetic induction using magnetic dust or iron fillings in water. First, we need to fill a clear container with water and add some iron fillings. Next, we need to place a magnet under or beside the container. Finally, we need to move the magnet around the container and observe the iron fillings aligning along the magnetic field lines. The motion of the magnet creates a change in the magnetic field, which shows how magnetic fields can influence conductive materials. Next, we are going to discuss about magnetic field and magnetic field lines. But first, let us know what a magnetic field is. A magnetic field is a region of space where a magnetic force can be detected. In this magnetic field, there are magnetic lines of force around a magnet. It's almost, however, attracted to the aroma of yummy food till a certain distance around the food. Here are a few important properties of magnetic lines of force. They are closed and continuous curves directed from the north pole towards the south pole of the magnet. Inside the magnet, the magnetic field lines are directed from the south pole towards the north pole, and thus a closed and continuous curve is formed. The tangent at any point on a field line gives the direction of magnetic field at that point. They never intersect one another. If two field lines intersect, there would be two directions of the magnetic field at that point, which is not possible at all. Speaking of magnets, did you know that the Earth itself acts like a giant magnet? The Earth behaves somewhat as if it has a powerful bar magnet at its center. Similar to how a bar magnet has two poles where its attraction is the strongest, so does the Earth, and its two magnetic poles are near the two geographical poles north and south. All magnets have north-seeking and south-seeking poles. We have placed the magnetic needle here. Note the direction. Now we shall float another magnet on water and see how it aligns itself. The magnet rotates while floating and settles in a particular direction. The explanation for this phenomenon is that when you compare the alignment of a bar magnet with that of the needle of a compass, they are similar. Both of them are aligned in north-south direction. We know that a freely suspended magnet always aligns itself in north-south direction. As like poles of a magnet attract each other, if a magnet aligns itself in north-south direction, it implies that the north pole of a magnet is facing the south pole of the Earth's magnetic field and vice versa. So, when we align the north on the dial of a compass with the north on the magnetic needle, the other directions east, west and south are identifiable. So get yourself a compass and find out the direction of the moonrise and moonset, or say which direction is the wind. Now we already know that the Earth itself behaves as a giant magnet and has a magnetic field of its own. Now similar to the Earth, the Sun also has its own magnetic field. The Sun's magnetic field is a powerhouse that impacts both our technology and natural phenomena on Earth. The Sun's magnetic field sends out charged particles known as solar wind, which creates space weather. When these particles reach Earth, they can cause geomagnetic storms that interfere with GPS signals and space weather patterns. These storms can also create beautiful auroras when they hit Earth's magnetic field, which shields us from solar radiation. The Sun's magnetic field affects the Earth's magnetic field, leading to disturbances based on the alignment of two. So that's all for today. We'll learn more about the magnetic effect of current in the upcoming video. Stay tuned.